Hello, 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 chemists, and welcome back to a new lesson on something called Charles' Law. You may remember from a couple days ago we looked at something called Boyle's Law that figured out that pressure and volume are related and that when one goes up, the other goes down. What about volume and temperature? What could happen there? Take a second and think. Let's say you had a container that the lid could move on. If you increase the temperature, do you think the volume would go up or down? And why? Here's what we're looking at. We have a volume and temperature going up in a direct relationship because as you increase temperature, average kinetic energy increases, like we know, which increases the space between molecules, which makes them get further apart, which makes the volume go up. that's what our topic for today is, and that's what we're going to dive right into. So, chemists, welcome to Charles. So, Jacques Charles experimented with volume and temperature of a sample at constant pressure, and he plotted the data. And it was just a nice straight line. Remember how back on Boyle's Law we had to do the whole inverse thing? Here it's not inverse. As temperature goes up, so does volume. So a linear relationship emerges. Slope is constant and predictable. And we have a constant rise over run and a constant velocity over temperature ratio. Not velocity, I don't know why I said that. Volume. Excuse my V. I'm still locked into like doing motion units. But yeah, so we have a constant volume and temperature relationship here. And this, by extension, got changed into William Thomas. So here we're working with volume and temperature, just showing as you increase the temperature, the volume goes up. But what we're really more interested in is what happened later. You see, based on the time serum, keep jumping, but this was like in the early 1800s. And later on, we went a bit further with this in like the late 1800s with William Thomas, who's also known as Lord Kelvin. You go to Kelvin. so, so this is the guy that our school is like actually like named after. You may have heard about that, but we have a nice scientific name in our building, and he recognized the significance of that whole thing that Jacques Charles did, and he noticed that predictions fail in the negative Celsius temperatures. So this value here of negative 273 degrees Celsius is where all these predictions of temperature and volume kind of stopped working, and it crossed like into a weird thing where you'd get like negative volume, and negative volume doesn't really make sense. Like you can't have negative a liter or something. I don't know. I don't know what that even means. Try to like get your brain to think about that one. So this whole relationship mapped out to negative 273 degrees Celsius. And Lord Kelvin, William Thomas, the guy our school's named after, recognized its significance. He created the Kelvin scale, where 0K represents the lowest possible temperature, negative 273 degrees Celsius. And this whole 0K thing in Kelvin is something you're going to see a lot in science and chemistry because it's kind of like a more accurate measurement of temperature when we're starting from as low as it can go and going up like as high as it can go, which is like infinitely high. but we start at the 0 point. Celsius, just to qualify why we use it, it makes more sense for us as humans, right? Like zero is like around freezing and negative 20 is cold and like 20 is hot. It makes more sense than saying 273 is freezing, 298 is hot, and like 255 is cold. Like the numbers are high and they're more confusing to use in day-to-day life. But when we're dealing with chemistry, this whole Kelvin thing becomes very useful because it's more representative of this graph. You see this like zero line for Celsius just splitting like this graph right down the middle? If we imagine that's not there and just use Kelvin, it becomes a nice straight line which is easier to work with. So we're going to do that. Um, and he called, you may have heard of this term or like heard it in sci-fi or something, but absolute zero is where molecules just stop moving. It's a lot colder than like where ice melts or anything. It's all the way at negative 273 degrees Celsius, which is 0 Kelvin, aka absolute zero. The absolute zero leads to like the whole ideal gas model that we mentioned very briefly, but this is like the idea that about gases movement and kinetic energy that we were sort of talking about last week. But the ideal gas model predicts that with zero kinetic energy comes zero volume, which doesn't make sense, and suggests particles that the particles will be non-interacting, which isn't true. Model predictions are a good approximation of this real gas behavior, but it fails at extremely low temperatures or very high pressures. It works really well in like this middle ground that we normally live in. And we have this whole thing. This is just kind of an introduction to this. Don't worry too much about this right now. But an ideal gas has no intermolecular forces, and real gases do have intermolecular forces. Even though they're very weak, they still act on each other a little bit. But Charles' law says the volume of a given amount of gas varies directly with the temperature in Kelvin when held at a constant pressure. So this is saying that if you were pushing down with 1 atmosphere of pressure on a container that had like a movable lid or whatever, at half the temperature you'd have half the volume, and at twice the temperature you'd have twice the volume. So V is proportional to T directly. I was speaking about pressure earlier, that's because pressure and volume have a relationship, but Charles' law speaks specifically to the volume and temperature. You'll see as a little preview of next week, we're going to combine these all together and get something that incorporates volume, temperature, and pressure. But for now, we're just going to think about volume and temperature. This is something that I'd very much like to draw all of your attentions to, because this is the first thing that you're going to practice in your booklet, and the first thing that we really have to think about as we're approaching these problems is that Kelvin is what we're going to use. And you might often get measurements in Celsius in questions, or if you're using a thermometer, or really in your day-to-day life, and it's up to you to notice that they need to be in Kelvin and convert them accordingly. So we have this little formula, which is also written in your notes, that says the temperature in Kelvin is equal to the temperature in Celsius plus 273. And you can just like move this equation around to figure out that the temperature in Celsius is the temperature in Kelvin minus 273. So here's like, don't even worry about Fahrenheit, but the boiling point of water is 100, and the freezing point is 0. And then in Kelvin, that's 373.15 and 273.15. This constant actually has a 0.15 on it. If you want to be super exact at any point, you can use that, but like the 273 for our intents and purposes is fine. Yeah, so let's take a look at how this is all going to come together for Charles' law. Just reasoning without doing too much of the math here. What is the new volume of a 40 liter of gas like container if the temperature in Kelvin is doubled? Remember, these are directly proportional. When one goes up, the other will go up, and they'll go up by the same factor. So we're doubling the volume, we're doubling the temperature. That means we're also doubling the volume. It's 2 to 2, so we'll end up with 80 liters. What if it's reduced to a third? Again, it's direct here. If we have a third of the temperature, we'll get a third of the volume. So a third, and 13.3 liters. That's a third of 40 for the people wondering where that number came from. But yeah, so if you're decreasing temperature by a third, it also decreases volume by a third. Now, here is our equation. Initial conditions are always equal to final conditions when divided, because we keep the same ratio. So we can figure out that V1 over T1 equals V2 over T2. This is the equation that we're going to use to solve these problems and use as our little tool from Charles' law to keep relating gases and how temperature and like volume and everything is all interconnected. This is slightly different than Boyle's law because now we're dividing on each side. We have a fraction on each side instead of just two things getting multiplied. So that just changes the way that we're going to solve the math a little bit. But make sure you write down this equation, make note of it, put it in your books, get it somewhere you can see it. This will also be written to you, but this is like the meat and bones of Charles' law as far as we're concerned. This is what we can use to figure some stuff out. And a little disclaimer, all temperatures must be in Kelvin. If you use Celsius, it's not going to work, so just telling you that now. Kelvin, 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 you go to Kelvin, so you should be able to remember that word pretty nicely. So what is the new volume of a gas if 100 milliliters of the gas at 25 degrees Celsius is cooled to negative 25 degrees Celsius? I'm going to give you an opportunity to try this on your own, but I will caution you, to be very careful about your units here. So take a moment, pause the video, and see what you can come up with by setting this up. Now see what you can come up with. So pause the video, and we'll come back in about 5, 4, 3, 2, 1. Okay, so our V1, 100 milliliters, it's saying that we're starting at 100 milliliters. And our T1 is 25 degrees Celsius, but we need that to be in Kelvin, so we're just going to add 273 to it. Boom, 298. Beautiful. Our second volume is what we're looking for, so we don't know yet. And our final temperature is negative 25 plus 273. We have to convert it, which equals 248. Watch your units. That comes flying in. So here, V1 over T1 equals V2 over T2. That's your equation, and we got to plug in all our values. First off, we can just like multiply this T2 up and move the equation around a little bit. Sorry, this is if we multiply by T2, we end up with V2 on itself. I'm going to slowly introduce these whole equation manipulations because they kind of make solving this all easier. So we're just going to plug in our values. 248 times 100 over 298 equals 83 milliliters, and that's your new volume. Beautiful. Decreasing the temperature by 50 degrees will cause a decrease in volume to 83 milliliters. So they're directly related. Here's another one. I want you all to try this on your own alongside. This will help you with your practice sheets and getting this all to make more sense in your brain. So here, if the volume of gas at negative 73 degrees Celsius is doubled to 48 liters, calculate the final temperature in degrees Celsius. So it's asking for Celsius here, so we have to make sure we give an answer in Celsius. But yeah, take a second, pause the video, try to line this up, plug into your calculators, and see what you come up with. I'll come back to you in about 5, 4, 3, 2, and 1. So we're going to predict again. We start with a V1 of 24 liters. We got that because it says the volume is doubled to 48, so you have to kind of do some reasoning there to figure out 48 divided by 2 is 24. T1 is negative 73 degrees Celsius plus 273 to make it Kelvin. Always make it Kelvin. Really going to emphasize that. And then you're going to make it 200 Kelvin. Our V2 is 48 liters. And then we have to find out the second temperature. Here, I think I skipped ahead a second there. Just watch how this equation moves alongside. We're just going to multiply by that T1, so we already have it. Or, like, we're going to have to do a couple manipulations. But here, this T2 can get multiplied over here. Then we're going to divide. Then we're going to divide. We're doing a bunch of equation manipulations here. You can plug this in however it makes sense to you, but I just want to play that back one more time. So how we're solving this before, we're multiplying by T2 to get rid of that, multiplying by T1, and dividing by this final V1. That's what we're ultimately going to plug in. If that doesn't make sense to you right off the bat and you want to start by just plugging in with the equation like this, you can do that. Eventually you're going to end up doing all those steps as you're solving your algebra, but it can be easier to isolate the variable you're looking for to begin with. So we're looking for T2 here. So we bring that up, and then we have to get rid of all this stuff to get T2 by itself. That's some math for you all. So like bringing that up, getting rid of the T1, and then getting rid of the V1. Then we're left with our answer. So then we can plug in all these values, and we get 400 Kelvin equals 48 times 200 over 24. Just plugging in these values. Then we have to convert this Kelvin to Celsius. So that's the opposite. Instead of adding 273, we have to subtract 273. Get left with 127 degrees Celsius. And I'll just draw your attention to the fact that Kelvin doesn't have the degree sign for whatever reason. It's just the K. And Celsius does have the degree sign. It's that little O with the C. That's another one of those convention notation things that you got to pay attention to. So just making you all aware again. Anyways, take a look at the stuff from the booklet. There's some practice in there, some problems, some math, some like graphs and stuff. It's nothing too crazy, but it'll take some time. So try to spend some time on that today. Tomorrow we're gonna dive more into these practice problems, and I'll give you some examples, and we'll have some further practice. Then come Friday, you'll have a little assignment to do. But with that all in mind, chemists, I hope you have a lovely day, and thanks for tuning in.